Just time, huh? Sure. All right. Anything you want to look at quickly? I don't have the test graded, so have to do something else.
Do we have a timeline on when this will be graded?
I've got other tests I'm graded, otherwise, grading, otherwise I could give you a better idea. No, it'll be next week, I think.
Okay.
That's
That's
what
okay.
I think. Yeah.
It's kind of that part of the semester where everything's just like crazy.
Yeah, well, the ones that I have to print off on the printer, they're all dark and pages missing, and it's, if I could just stick to people sticking to the page and not written notes, it would be a lot easier to grade, but it takes a long time this semester. So, well, we're starting the last chapter here today. This will be on vector fields and their applications. Don't let this sound hard. It's a very easy concept. A vector field is just a map or a function that associates with each point a vector. Exactly one vector. Now I said region as though it's a plane region. It could be a region in 3 space also, or whatever dimensional space, it doesn't matter. It's just a vector with each point. If you think about it, you can think of some vector fields already, like a gravity field, right? At each point, there's a gravitational force. It has a direction and a strength, right? So that's your vector. Or an electric field, right? You have a vector that gives the strength and the direction of the pole on a charged particle. So there's a simple example. Suppose I wanted to sketch the vector field. Which we'll say is on R2. What is R2? This is used in higher mathematics a lot, so I'm introducing it. It's just the plane, right? It means the reals, Cartesian product with the real, so it's the real plane. Meaning I put a vector at every point in the plane. Suppose it's this one. F of xy is equal to 2I. How about that? That's a really easy one. What do? You just go sketch a vector of length 2 in the x direction at each point, right? So here's this one. Oops. If this is the 1, 2, 3, make a vector of length 2 there. And what you do is you just go through and sketch some representatives. And so there's some representative vectors. You just sketch a vector 2 units to the right at each point. Some interesting ones come like this. What if f of xy is equal to minus yi plus xj? How do you? This one, however, has an interesting property that because f dot the vector at the origin xy out to that point is equal to what? Well, it's minus y x dot xy equals minus xy plus xy equals 0. Each vector in the vector field is perpendicular to a vector from the origin to the point. Also, you can say the length of this vector, of each vector in the field is what? It's the root sum square of the components. It's square root of minus y squared plus x squared. Oh, that's just the distance from the origin, right? Square root of x squared plus y squared. Now I know how to sketch it if I know how to sketch the length.
Hey, Dr. Stapleton, I think the camera is like automatically following you. So it just keeps shifting a lot.
I'm sorry. I'm sorry. I left the thing on auto track. Oh, I forgot to adjust the camera. My apologies. I hope that's readable now, is it? I hope.
Yeah, that's okay. Thank you.
Okay, yeah, thank you for commenting. I was not paying attention. Let me see if I can move this down where you can see it better. Still see it here. For this one, at each point x, y, what we can do is the length of the vector is its distance from the origin, so it's this length. And then it goes in the direction minus y x. So if y and x are both positive like this, I go in the negative direction, the amount y in the positive direction, and positive in the x direction. I go like this. It's supposed to be perpendicular to this vector from the origin, but the length of this vector. So it goes like that. I can draw one here. Continuously as they go around here, so they're all going the same direction. Out here, I'll get one that's perpendicular to the axes. It's the length down the axis. And so when you say sketch the direction field, that's what it means, is draw some representatives so that people can kind of see this like it was a flow field or something. And this one is a rotation, right? Because all the vectors are perpendicular to the vector from the origin, x, y. So that's one kind of vector that's especially important, is this rotational kind of field. Another one is this kind of field that you'll see in a lot of cases like gravity and so forth. F of x, y equals x, y over the cube of the length of x, y. So if you're at any point x, y in the plane, you take that vector x, y, and then I'll put a minus here, divided by its length. This is a cube. Minus x, y over the length cubed. And what is this look like? What's the direction of each vector? So sometimes you can plot by, like we did this one, the direction of the length. The direction is what? Think about what this is. This is just a number here, right? So we're dividing the vector x, y by this number, which is its length cubed. Gives you a vector in the same direction because it's dividing by a positive number. Now you put negative, this goes back towards the origin, right? Because it's a negative number times the original vector. Now, how long is it? Well, if you think about the length of the length, just like we were doing over there, maybe I should have said your direction was perpendicular to the vector from x, y, and then length, that the length here is, well, length of x, f of x, y, the length of minus length of x, y cubed times the vector x, y. Well, this number here is just a number, right? And so if you have a number times a vector, its length is the absolute value of the number. times the length of the vector. Oops, absolute value of the number times the length of the vector x, y, right? The cube of the length out of here and put absolute value on it, so now the minus can go away. Times the length of x, y, so the length is actually, well, length and length cubed is 1 over length squared. What does that look like? An inverse square law like gravity. If you now multiply this by a constant, you can get gravity. Multiply by the gravity, it has this kind of force, right? The GMM over R squared, where so it's this is the magnitude of gravity is this times GMM. Now this one actually points towards the origin, but the length is inversely proportional to the square. So you can sketch something. You sketch something like this. Out here, you sketch a vector that's not 1 over the square of the length of this thing. So if this is length 2 out here, then this is 1/4 long here. Let's say, suppose this is square root 2, then this is 1/2. That way it looks like what we have here. But if you're out here, 2 units out, then 1 over 2 squared is 1/4. Back to the origin, and all pointed at the origin. So little vectors out here, big vectors in here that go clear through. Sometimes you don't want to draw those because they make the picture messy. But that's the idea. Something like that. All the vectors pointing at the origin and getting very short as you go on, falling off is the square of the distance from the origin. There's the inverse square law that comes up a lot in applications. There's a rotational kind of vector field that comes up a lot in applications. But the idea is just to be able to have a feeling for what these look like. Sometimes you can figure out their length and direction and sketch them nicely. Or you get this nice constant vector field, and that's easy to sketch too. So much for sketching direction fields. There's nothing more than that. Just the idea is there's a vector at each point that represents the strength of gravity or the electromagnetic pole or something. Or it could be the flow field for a fluid, right? This is maybe a rotating fluid, and this is its velocity vector at each point, the velocity of the fluid. Now, there's lots of things we want to do with these. Recall the gradient of a vector. Gradient of a function f of x, y was the vector df dx df dy. That was the gradient. This suggests we do the following for just simplicity of notation. We define what's called the gradient operator. Operator is just like a function, but typically it's used when you map a function to a function. And so that's what this is. Gradient will denote the vector d dx, d dy. And you might say, well, wait a minute, that's not a pair of real numbers. It's a vector in the abstract sense. We've been dealing with vectors in the plane, so they're directed line segments. You can write their two components and say that's a vector. This is a vector in a more abstract sense. We won't do the definition in this class. You take advanced calculus or something, you see the broad definition. But it has components that are actually maps from functions to function. If you apply this to a function, you get out a function. So this is a function itself from functions to function. I'll call it an operator. Although people use operators in a lower sense than that, this is often a usage of it. And now we can say this represents the gradient of f takes a vector, takes a function to a vector. So you input a function and get out a vector. Moreover, in more generality, things like this, the divergence of a vector field. So a vector field here at f of x, y associates with each point x, y a vector, right? You can apply it to this, and this means when you write this div or for divergence, it means take the gradient operator, dot product it with the vector field. So it's like this, written out, and you're taking this vector dot the vector that looks like f1 of x, y, f2 of x, y. So let's write it out. It's in fact, let's put it up here. For a vector field in general, f of x, y, having components f1 of x, y, one of x, y is its first component. F2 of x, y is its second component. Here's what a vector field is in generality in the plane. It's just a vector gotten by taking a function of the coordinates for each of its components. So for this, what you're now doing is you're taking ddx, ddy, functions of x and y. And so you get df1 dx plus df2 dy. This actually outputs a number at each point x, y. So we call it a scalar field. Right? Remember, in the context of vectors, numbers are called scalars. This outputs a scalar or a number at each x, y. It's just an ordinary function from right, a function of two variables. Function of two variables. Sometimes called a scalar function. Scalar value. Let's look at that one. Instead of vector value function, scalar value function. So we can take the divergence of a vector field or the gradient of a scalar field. And there's some other definitions that are made, and all these turn out to be useful in lots of applications, is why we're introducing them. Let's just do a simple example before I get on to some more. Have f of x, y is x, y, I minus y squared j. What is the divergence of f? Well, again, it's just, this is f1, this is f2, and the divergence is very easy. You just take df1 dx plus df2 dy according to the definition. And then partial of xy with respect to x plus partial of minus y squared with respect to y gives us the ordinary scalar function y minus 2y or negative y. Which comes out with a function of two variables. In this case, the x fell out. There's divergence. Then you can do the following. The Laplacian after Simon Laplace. Has this named after the Laplacian. Book has a funny write-up on it. they say he was kind of vain at some time and part of it, but at the same time, he once wrote to somebody, read Euler, he's the master of us all, so he at least recognized Euler was a better mathematician. The Laplacian is the following, we write del squared. And this means del dot del. And we can apply that then to a function. Suppose I take del squared of the function xy plus y squared. Something similar to that last one. What do I get? Well, del dot del means you just take the gradient ddx dy operator dot with the gradient operator ddx dy. And what do you get if you dot product? You get this one with this one is d squared x d squared dx squared. And then plus this one with this one, d squared dy squared. So we'll plus d squared dx squared of the function plus d squared dy squared of the function. And if you put Laplacian equals 0, it's called Laplace's equation. It's something that's really useful in all sorts of scientific applications. For instance, steady state heat distribution on a plate satisfies Laplace's equation. The heat distribution over the plate is this thing equals 0. So xy plus y squared, xy plus y squared. There's all it is to Laplacian. You take second derivative with respect to x of the thing plus second derivative with respect to y of the thing. And that function that you get, let's see, y plus 0 plus this one, x plus 2y gives us x plus 3y. There's the Laplacian of this function here. So these are just a whole bunch of definitions, and it's probably hard to imagine why these are so useful. I'm just trying to add a few comments to suggest that. And you can do these in any number of dimensions also. That's what we want to do next. These all extend to 3 dimensions and more. You have the gradient operator is now the vector of 3 components, ddx, ddy, ddz. The divergence of a vector valued function f, where now f of x, y, z, a function of 3 variables, has 3 components. A function f1 of x, y, z, function f2 of x, y, z, and a function f3 of x, y, z. So it's a vector. It assigns a vector to each point x, y, z, right? You put an x, y, z, and this gives out a vector. That's the vector field in 3 dimensions. Now, if you take the divergence of f using this, I guess we should give the other notation too. Using this gradient with 3 components, now it's just df1 dx plus df2 dy plus df3 dz. The same thing as we did before in 2 dimensions, just with 1 more component. How easy, right? And the Laplacian comes out del squared of a scalar function f becomes d squared f dx squared plus d squared f dy squared plus d squared f dz squared. Just has 1 more component. Right, space time or something. It's just for fun. Can you imagine what this means? This has another notation for the Laplacian, maybe I should introduce. Sometimes I'll write del squared thinking of del dot del. For short, they'll just use this operator, del, instead of delta, instead of del squared. And So you can say here's del F, or it's the Laplacian of F or del squared F. It's just different notations for the same thing. In 4 dimensions, they like to write this. The box F is the 4-dimensional Laplacian. So you can extend these into higher dimensions. But now, once you get into 3 dimensions, remember we have another product besides the dot product, and when we get to 3 dimensions, we have the cross product also in 3 dimensions, right? Well, I'm sorry, this is so rote definition. Stop me if it gets confusing or too much. Also in 3D, there's a cross product, where we can define what's called the curl of a vector field. This is real important in doing rotational dynamics, and it's also used in electromagnetism. Have you seen Maxwell's equations before? Absolutely fundamental. They're great videos. And it underlies, Maxwell's equation underlies all your electrical devices and everything. And the equations have curl in them. Some of them do. Curl F is gradient cross F. And so what is that? Remember cross product? Sound familiar? What you do is you make this determinant I, J, K in the first row, and then you put the gradient operator in the second row, ddx, ddy, ddz. And the order is important, right? If you interchange 2 rows of a determinant, it changes the value of the determinant by -1. So you put them in the gradient and then the F. F1, F2, F3, where F1, F2, F3 are these functions that are the components. And that defines the curl, right? If you like, you can write it out. I think it's sometimes faster to just write it out without putting the determinant in the middle. Right? It's I times this operating on this minus this operating on this. So it's df3 dy, this one on this one, minus this one operating on this one. df2 dz, y and z. And then you have df3 dz. You're taking this on this minus this on this minus j. So you get df3 dz minus, I got this backwards. Yep. Should be, yeah, df3 dx minus df1 dz. And then this on this, df2 dx minus df1 dy. So there it is written out. So in 3 dimensions, you can do the divergence of a vector field and also the curl of a vector field. I suppose we ought to do an example for that. Yeah. Suppose we have the vector field in 3 dimensions. Let's see.
Does the middle term, like the j term of the determinant, have to have be multiplied by -1 or no?
Yeah, and it is, I think, right? Did I put that backwards? Yeah, it's supposed to be -1 in here. df1, thought I did that. I didn't pay enough attention. df1 dz minus df3 dx. Yeah, thank you. Minus this on this, and then minus the whole thing, yeah. It's 3, 1 minus 1, 3, yeah. Okay, so if F is this vector field, suppose I gave you 6xy minus y cubed, 4y. Oh, that one's gonna be too long. xy YZ and XZ. Suppose I give you that vector field. At each point X, Y, Z, it assigns a vector, right? Suppose I take the divergence of F. Well, I just take ddx of the first component, plus ddy of the second component. Divergence is very easy. Plus ddz of the last component. And I'll wind up with, let's see, y plus z plus x. There's the divergence, is that simple, folks. Now I go to compute the curl, it's gotta be a little longer. Curl of F just computes as, each one is a dy minus ddz, 3 with 1, ddz minus ddx, 1, 2, ddx minus ddz. First component goes like, for component 1, you put 2, 3. Component 1, you put 2, 3. Component 2, you put 3, 1. And component 3, you put 1, 2. It's just a cyclic 1, 2, 3. Rotate this around to the end. Rotate this around to the end to get the last one. So you keep track of them that way cyclically. 2, 3, 3, 1, 1, 2. Then you got to put the corresponding components up here. You got to put the F3 here with the Y, the third one with this one, and then F2 with this one. And with this one, you need the F1, and with this one, the F3, and with this one, you need the F. So this is 1, 2. It's ddx minus ddy. df2 and df1. So what are we going to get now? We're going to take derivative of xc minus derivative of yz with respect to z. And then we're going to take derivative of f1, that's xy, with respect to c, minus derivative of f3 is xc with respect to x. And finally, df2 is partial of yz with respect to x minus df1 is yxy. Take with respect to y. So it's like 3, 1, 3, 2 should be 3, 2, 3. One, 3, should be 1, 3. Good. All right. And then this comes out just to be 0 minus y. This one comes out to be 0 minus z. And this one comes out, let's see, to be 0 minus x. Ordinary function of the curl is a vector.
Could you explain the 1, 2, 3, 2, 3, 1 process again?
Oh, yeah,
Like,
sometimes, well, I don't do this as much with curl as I do with products of vectors, but when I take the cross product of vectors, V with 3 components, cross W with 3 components, sometimes rather than writing out the determinant, I like to do it quickly by saying you're taking cyclic permutations, that is cyclic orderings of the numbers 1, 2, 3. When I want to write this cross product, for the first component, I use the 2, 3 minus 3, 2. So I'll take V2 W3 minus V3 W2. So first component I use 2 and 3. So it's a 1, 2, 3. Then I rotate this around and call this 2, 3, 1. So the second component I take 3, 1 minus 1, 3. So I'll take V3 W1 minus V1 W3. Then for the third, then I'll rotate this around, permuting them by it's changing the order by rotation. So it's a cyclic permutation. They call it 3, 1, 2. And then for the third component, I take 1, 2 minus 2, 1. So I take V1 W2 minus V2 W1. And that takes into account minus on the second component from the determinant. But it's a 1, 2, 3 kind of thing. First component you do 2, 3 minus 3, 1. 3, 1 minus 1, 3. Third component you do 1, 2 minus 2, 1. That's kind of an easy way to do it. And I was doing that a little bit with here, but it's more confusing in the curl because you have this is 2, 3 working upwards minus 3, 2 working upwards. So it's a little more awkward. Okay?
Yeah.
But there's all those introductions. Then I talk about conservative vector fields. The first section is basically chock full of definitions, and then you use them later. So I can say, why are we doing all this stuff right now is a good question, but it will come around. A vector field in any number of dimensions is said to be conservative on a region if it is the gradient of some function on the region. Now you can start to see this is going to be useful because conservative vector fields are like gravity, right? Gravity is a conservative vector field. For instance, if it is the gradient some function on that, some scalar value function on that region. And this can be in any number of dimensions, 1, 2, 3, and so forth. And the nice thing is that conservative vector fields have a potential energy. And so this plays into the concept of potential energy. Here's an example. Show that this vector field F equals 6xy minus y cubed for first component, 4y plus 3x squared minus 3xy squared is conservative. Thinking of a conservative force, maybe F is a force, this is a conservative force. How do we show it's conservative? We have to show that it's the gradient of some function. Of xy. Maybe I should write that over here. If it's the gradient of some function of the region, in other words, F of whatever number of variables it is equal to the gradient of some function phi. If it's a two-dimensional, F of xy equals gradient phi of xy. So we'll write that over here. We need gradient of phi equals F. But the gradient of phi in 2 dimensions is d phi dx, d phi dy, right? Needs to be equal to this function up here, 6xy minus y cubed, 4y plus 3x squared minus 3xy squared. we'll be conservative if and only if we can make this work. Well, two vectors are equal if and only if all their components are equal, so we need the phi dx equal the first component, 6xy minus y cubed, and we need the phi dy equal the second component, 4y plus 3x squared minus 3xy. This is the first one we've actually had to do a problem with, just a calculation. How can we solve for phi? Phi has to satisfy both those equations. From the first one, we need phi equals, I'm going to put two of these, one for each of these two equations here. If this is the partial derivative of phi with respect to x, then phi must be the partial integral with respect to x. 6xy minus y cubed dx. And it's not marked any differently, but it's still called the partial integral. So I'll write it over here just to remind us. I mean, treat y as a constant when I integrate with respect to x, so if I take the derivative of the resulting function, it will give me this integrand back. Well, the partial integral of 6xy with respect to x treating y as a constant is just 6 times x squared over 2y, or 3x squared y. Right? And partial integral of minus y cubed, well, y is treated as a constant, so it's just minus xy cubed. Right? Think of minus y cubed as c, and so this is x times c. And then there's an arbitrary constant of integration, right? But y is a constant within here, so actually what we're talking about is an arbitrary function, g of y, is the constant of integration. The idea is these are all functions whose partial derivative with respect to x gives you this integrand back. Partial of this with respect to x gives 0 as we want. Partial of right, yeah. And partial of this with respect to x gives the 6xy. Sure enough, those are all functions whose partial derivative is 6xy minus y cubed. Also from the second equation, by partial integration, I integrate 4y plus 3x squared minus 3xy, treating x as the y as the variable and x is a constant, right?
You dropped a squared on the y.
Thank you. Yeah, I dropped it right here, didn't I? There's a square. So integral 4y then gives me 2y squared, treating y as the variable, but minus plus 3x squared, treating y as the variable is just a constant. So you get plus 3x squared y. All right? 3x squared is like c, since x is treated as a constant. Integrated as c times y. And then minus 3xy squared, treating x as a constant, is minus 3x times y cubed over 3 is minus x y cubed. All right? X is treated as a constant, and the integral of 3y squared is y cubed. And then finally, x is treated as a constant, so your arbitrary constant here of integration can be some function, let's call it h of x. An arbitrary function of x goes there. F will be conservative if and only if a phi exists that satisfies both these equations. Can I satisfy both these equations? That's what the trick is. I have to do to make both these equations whole. Well, I noticed there's a common term here. That's good. Those match up. And let's see, there's a common term here. These match up. What I need is this function g of y, which is arbitrary at this point, to match up with this and this, right? Oh, sure enough, if I let g of y be 2y squared plus an arbitrary constant, then I can make this work. So g of y must match up with 2y squared, and then there's also an arbitrary constant, g of y equal h of x is a constant. And so the most general function I come up with satisfying these two equations is that phi of xy can be equal to, let's see, 3x squared y. What you do is you copy one of these down, minus xy squared, and then you take all the terms that weren't there from the other one, there's the 2y squared. And then there's always a plus c, a real constant that doesn't depend on either x and y at the end. Those can go into both of these. So here, this one works. This satisfies both these equations. And this represents all potentials. So maybe I should put that down. A vector field F is conservative on a region if it is the gradient subfunction, F equals gradient phi, in which case then phi is called a potential for F. Why a potential? Because there's always a plus C on the end.
Can you,
Oh yeah, I need to move this back, thank you, yep. Let's do that. Then phi is called, so I put this in here, a vector field F is considered a region if it is the gradient of some function phi, like on the region, F equals gradient phi. Then phi is called a potential for F. And there's an infinite number of them, but they're all equal to within a constant. Does that sound familiar? All the functions equal within a constant? Sure it does, right? Calculus 1. Right? You take an integral, all integrals of a continuous function, for instance, are equal to within a constant. This is actually going to generalize the fundamental theorem of calculus. How about that? We'll call it the fundamental theorem of line integrals when we get to it. It's basically a fundamental theorem of calculus with components. So we're coming up on that, but that's the thing, it's the same thing. Just like all antiderivatives of a function are equal to within a constant, all potentials of a conservative vector field are equal to within a constant. And so we found a potential, consequently, conservative vector field. Most of the time, if you just write down an arbitrary vector field, it's not conservative. So this works, that is, F as given is conservative. Found a function whose gradient is F. That's the idea of a conservative field. It's conservative if and only it's the gradient of some function. I think I'm going to pass on the other stuff. Maybe I'll just note it that unless I spend too much time on this. But we can just make a note. Do you remember the scalar triple product? You could take three vectors, U, V, W. Sometimes they put commas between these. The triple product of vectors, or scalar triple product. How was remember saying this before? Scalar triple product is U dot V cross W in 3 dimensions only, because the cross product is only defined there. So in 3 dimensions, we let this. Does that look familiar? Oh.
Kind of does,
Yeah.
sort of.
Well, we'll define it this way now. This is the scalar triple product. This is triple vectors product. And the output is a scalar, because you take the cross product of these, you get a vector, then you dot product with this one and get a number. Well, this extends to vector fields now. Leads to gradient dot curl and if you think about it, what does this have to be like? This always comes out to be by the we'll do this. It's ddx dy gradient operator. And then you dot product it with this determinant, that's the curl. I, J, K, DDX, DDY, DDZ. Right? And then F1, F2, F3, the components of the vector field. And guess what this always comes out to be? Yeah, 0, good. That's a judicious guessing there. So yeah, what you do is if this is dot product, what you can do is just replace I with this, replace J with this, and replace K with this, and you'll get the result. It's the same as the determinant. Maybe you remember this from before. It's DDX, DDY, DDZ, replacing IJK. Then you got DDX, DDY, DDZ here, and F1, F2, F3. Maybe one thing you remember about determinants is when any row repeats or any column repeats, or it's just a multiple of each other, the determinant is always 0. If you compute this out, you'll always get 0. And so we say that the gradient of the curl is always 0. The theorem then. For a twice continuously differentiable functions, you can take those and get. And then you can do a triple vector product, curl with a curl of F also. Let's just leave that there. And then that's the end of the section. Rest of the class, I want to move on to the next section a little bit. Those are just kind of introducing a lot of definitions that we're going to use. The drawback is that after doing all that, the book then changes gears and goes on to a seemingly unrelated topic. But then it comes back and starts to use this in ensuing sections. So the next topic is line integrals. And this will take up the rest of this lecture and the next one besides at least the rest of these 2 lectures. And then we'll get back to this topic because it's used in a lot of line integrals. All right, I've got it started over on the board on the side here. Maybe I should start by introducing that. This is the handout if you want. There are actually 2 types of line integrals that are in common use, the scalar line integral and the vector line integral. So you'll see both of those. And then there's multiple notations for the vector line integral. But just keep in mind that all these boil down to just these 2 integrals, and this one's defined in terms of this one. So the scalar line integral is actually just sort of a nice, easy generalization of what you did in calculus 1, and it has this notation here. And I'll say intuitively, it's if you're given a vector valued function, R of t, which is x of t times I, E1 for the elementary vector I, and E2 for elementary. X of ti plus y of tj. So you're moving along some curve given parametrically this way in the xy plane. You want a line integral along that curve. You just kind of curve the integral that you had in elementary calculus and do the same thing you did before. You take the area of the rectangles added together. Let's move it down here. Instead of integrating along the x-axis, you now integrate along this curve C, which is given parametrically like that, some function of ti plus some function of tj. And you partition this little interval up. I guess I started this into that. X1, Y1, X2, Y2, X3, Y3 points along this curve when you put in various values of T0, T1, T2, give these points along the curve. And then, instead of taking the height of rectangles up to a function of X, you take height of rectangles up to a surface, Z equals F of X, Y over it. And what you get here is an estimate for the area of the curtain hanging down from that surface down to the curve below it. And if you take the limit as the number of rectangles goes to infinity, you get what's called the line integral. So it's just a generalization of the definite integral in calculus 1 to take rectangles along the curve and take the area of these kind of curled rectangles instead. Well, what's the area of a curled rectangle? We'll go down a little bit here. I'm gonna push this down a little bit and say, here's the definition. That's too much. Let's just say what you do is you have a parameter for these points, right? This is X of T1, Y of T1, X of T2, Y of T. Break, I should say Tn equals B. So you go from T0 to Tn with partition the T interval for the parameter from T0 to T1, T1 to T2, Tn minus 1 to Tn. With T0 equal A and Tn, it should say equal B. Then there are n corresponding lengths of arc, right? Delta S1 is the length of this first arc, delta S2 is the length of the second arc, delta S3 down to delta Sn. And if you want the height, the area of the curled rectangle, you just take base times height. And the height you can take at any intermediate point on the kth interval. So on the kth interval here, you take any point you want, x k star, y k star, and take the height of the function of that point for the height of the rectangle. And then that gives you the area of a rectangle up to the surface. And you take tk star, the point of the kth interval, arbitrary, and then I'll try and write something on the board too. This is what you get then. The scalar line integral, which we give it this notation, right? In calculus 1, you say integral from A to B, f of x dx is a function of one variable. For a line integral, say many variables it is, because it's in multiple dimension space, such that there was in the plane, the f of x1, x2, is equal to the limit as the number of subintervals goes to infinity of the sum, k equals 1 to n rectangles. Base of the rectangle is the length of arc times the height is after some intermediate point. So that's the definition of the definite scalar line integral. That makes sense, sort of? T runs over some interval a to b, and you add up all these, partition that up and add up all these rectangles. Okay, well, maybe you remember what's the arc length of a curve, kth interval, delta sk. This is the arc length of the kth interval, can be gotten by integrating from tk minus 1 to tk, the length of r prime. That's how you compute arc length, right? It's the integral of the length of r prime gives you the arc length along the kth piece. And so you can replace the when you put that in for delta sk and take the limit, what this comes out to be is that the line integral as defined, the limit of that sum, is actually equal to the value of f of r prime dt evaluates the line integral. This represents the limit of the area of the rectangles below the surface. Let me write that on the board, then use the summarize the notes too. line integrals, the scalar line integral. Why would they call it scalar line? Because it's line integral of a scalar function. Is defined to be along a curve C given parametrically by some vector valued function R of t. This will be in 2 dimensions here. Let's do it in 2 dimensions. R of t equals x of ti plus y of tj. Is obtained or defined by, here's the notation for it. And it should be of a function f of x, y of 2 variables. So the scalar line integral along a curve of its function of 2 variables is defined by it line integral f of x, y ds is the notation. It's supposed to be the limit as the number of increments goes to infinity of the sum k equals 1 to n f of x k star y k star any point along the k piece delta sk where t is partitioned. I shall put that up here, a less than or equal to t less than or equal to b. The interval a b is partitioned into subintervals t0 to t1, t1 to t2, down to tn minus 1 to tn. Star yk star is any point in the kth subinterval x of tk star y of tk star at any k star in the kth interval tk minus 1 to tk. And delta sk is the arc length of the kth subinterval. Kth arc length. Which remember the definition of arc length is the interval from tk minus 1 to tk, length of r prime of t dt. And so then this is the height, the kth height of a rectangle. This is the kth base. And this amounts, taking a curve C, but down by R of t less than or equal to b. Here's the point x of t, y, x of a, y of a that begins the curve. Here's the point x of b, y of b ends the curve. We partition this up. Here's x of t1, y of t1, all the way down. This one is x of tn, y of tn. Partition, and there's a surface over the top. t equals f of x, y. And you're taking on each interval some intermediate point, the height up to the surface, and then taking a curved rectangle like that, taking its area. And you take some height on the second rectangle, so this is partitioned up into little points here. And the second rectangle, you take any point, go up to the surface, the height of the surface there, and take a curled rectangle over that. All the way down to this one, give some curled rectangle up here. Some of these areas correspond to these. You take the base times height. And then I said, this is equal to the limit that then goes to infinity of the sum k equals 1 to n. Well, let's just write that as a theorem. Theorem for R of t piecewise, well, R of t smooth, meaning it has a continuous derivative along C, and F continuous. You can evaluate the scalar line integral. F of x, y, scalar function, f of x, y, ds, as being the integral t going from a to b of f, a function of x of t, and y of t along the length of r prime of t, dt. That'll be the formula for evaluating. Okay. So just for a real simple example. We're going to evaluate this line integral of x minus square root y dx, that line integral, along the curve given by x equals 2t, y equals t squared, t running between 0 and 1. So this curve is a parabola, if you think about it. And I integrate along the parabola, the area below the surface z equals x minus square root y. And let's do it for t going from 0 to 1. Okay. How about that? We just have to get used to the theorem here. Is you rewrite this as the integral t going from 0 to 1 and write x and y as the functions of t they are. X of t is 2t. Y of t is t squared, so we got square root of t squared. There's x minus square root y. And then ds gets replaced with length of r prime dt. That's ds. Well, what's r prime? R is the vector valued function x and y, so it's 2t squared. And if I take r prime, then that's the square root. R prime is 2t. And the length of R prime, we can calculate as in the root sum square of those. 2 squared plus 2t squared is 2 times the square root of 1 plus t squared. Let's see, square root, yeah, 2 times square root of 1 plus t squared. But now I put that in here. This is the integral from 0 to 1 of 2t minus square root of t squared is absolute value of t. I can just put t because t is not negative on here, so square root of t squared. So 2 square root 1 plus t squared, and then I'm getting integrated with respect to t. Well, that's not too bad. This just comes out to be t. And I've got integral from 0 to 1 of square root 1 plus t squared, 2t dt. Must be a Cook problem, right? Because there's an obvious substitution. I can let u equal 1 plus t squared. Whenever you have a function of a function, you think, what if I let u equal the inside function? Then du would be 2t dt, derivative dt. How lucky. There's du right there. So this is integral of square root of u du by u substitution, right? And then if t is equal to 0, then u is 1 plus 0 squared. T equals 0, and the u equals 1 plus 0 squared is 1. So the new bottom endpoint is 1. If t equals 1, the top endpoint, then u is 1 plus 1 squared is 2. So the new integral goes from 1 to 2. And let's see, integrate that, I get 2/3 u to the 3/2. For that, I need to plug in 2 and 1 and take the difference, right? So I've got 2/3 times 2 square root 2 minus 1. How about that? The area of that one. What is it we're doing if you want to think of this geometrically? You've got a curve here that you can sketch pretty easily, right? If x equals 2t, y equals t squared, then we have that t equals 1/2 x can be substituted into here. And we got y equals 1/2 x squared. It's the curve y equals 1/4 x squared, right? T going from 0 to 1 means x goes from 0 to 2. And so it's this parabola. Goes to the point 2, 1 here. 1/4 x squared. So there's my curve C. Sometimes we like to put the direction of motion, t going from 0 to 1 forces it to go this way. So we'll put that. That's my curve C. And what I'm doing is finding the area below that surface over this curve, if you want to think of it as a geometry problem. Actually, what you'll find is this is a more general domain than just the height of the curtain. Remember, one dimension, if you wanted to find the mass of a rod, how did you find the mass of a rod if you had its density function, let's say delta of x? The density of x. What was the mass? That one? It's just the integral of the density. This goes from x equals a to x equals b along the x-axis. And just integrated from a to b the density gave you the mass of the rod. Right? Now can you imagine how this plays into that? You can treat this as like a y or a one-dimensional object. Now, this is formerly. Now you can have a curved wire. If you have a curved wire, you can take delta of xy equals mass at the point XY of a wire. Not mass, density, I'm sorry, density. And the mass of the wire is equal to the integral t going from A to B. If you have the wire as a curve of R of t, t running from A to B, then the mass is the integral from A to B of the density function at x of t and y of t. Oops, I'm doing the atomic. It's the line integral delta of x, y, ds. Sorry about the evaluation. So you just take this one and redo it. You can do curved wires instead of just straight wires. So it has those kind of applications in addition to getting curved. All right, I did that because I just had a few minutes left. I couldn't start the next topic. Line integrals is actually a rather long topic. So we'll get into it next time. It's the beginning of the notes. Maybe I'll update the notes slightly even. And let's see, here's some problems then we'll look at. Out of 15.1, all these definitions of gradient and curl and divergence and triple product. Let's look at all these problems, but they're fairly short. 5, 6, 7, 8, 15, 16, 19. Doesn't hurt to do more. 33 and 37. All right. If you want to start the line integrals, we haven't gotten very far. A lot of these are vector line integrals. Maybe let's just give the first two. Trouble is, I can't remember which one are scalar line integrals. So this will be to be discussed. We haven't done the vector. But 1, 7, 9, if you want to work ahead. 11, 13 AB, 19, 23, 27, 33, 37, 41, 49, 51. These whole things to be done yet. We're gonna have to probably do 2 of these or so far. But if you want to look ahead, there's more. Good evening, everyone.